Hi, everyone. Let's continue our discussion. Um, we're going to look at greedy versus dynamic programming. Um, we're going to use a knapsack problem as an example. In the knapsack problem, we want to pack items selected from a given set of items in a knapsack, as many as possible. Okay, in particular, let's say we assume we have n items. Let's call them A1, A2, up to AN. And the i's items has a value. Say A1 has a value V1, A2 has value A2, A2 has a value A2, and AN has value VN. And also each item has a weight. So let's say A1 weights W1, A2 weights W2, and AN weights WN. And we have a knapsack. The knapsack can hold at most W pounds. And we assume that VI, WI, and W, capital W, are integers, positive integers. Let's look at 0, 1 knapsack. In this problem, each item is either taken or not taken. That means we cannot break an item into smaller pieces. They have to remain to a whole. So that's why it's called 0, 1. And we have a different version of knapsack problem that is called fractional knapsack, which means that each item, or some items, can be further divided into smaller portions, meaning fractions of items can be taken as long as there is room in the knapsack. So both of the problems are maximization problems, and both exhibit the optimal substructure property. And for 0, 1 knapsack, if item J is removed from an optimal packing, the remaining packing is an optimal packing with weights at most capital W minus WJ. So that's how much the J's item weighs. In the fractional knapsack, if W pounds of item J is removed from an optimal packing, the remaining packing is an optimal packing with weight at most capital W minus small w that can be taken from other n minus 1 items plus Wj minus, so this would be minus because we remove W, so this could be fraction. So the item now, we still have Wj minus small w portion of item J left, so we can still pack if there is room. That's 0, 1 knapsack. Now let's look at a greedy algorithm that solves fractional knapsack. The idea is straightforward. First of all, we want to find out the unit worth, so which means that we want to find out the value per pound. So then this indicates how valuable item I is. Then the greedy choice would be, we'll take the items as many as possible with the largest unit value or the value per pound. If the supply of that item is exhausted and there is still room, then we'll take as many as possible of the item with the next largest value per pound, and so forth until there is no more room. We can, for instance, if the knapsack has some room left, and the next item weighs more than that room, so then we can just divide that item into smaller, cut it into two parts. One part fits the room exactly. So then this is a optimal solution, and the runtime is to sort, because we start from the largest value per pound, from the item with the largest value per pound, so which means that this involves sorting, and sorting takes the order of n log n time, and after that, greedy algorithm is a linear time, so the running time is in the order of n log n. Now let's see that the greedy choice fails for 0, 1 knapsack. Again, we use an example. So here is the example. So we are given a knapsack which can hold up to 50 pounds of goods, and we have 3 items. Item 1 weighs 10 pounds, and it has a value of $60, and item 2 weighs 20 pounds and has a value of $100, and item 3 weighs 30 pounds and has a value of 120 pounds. So we figured out its value per pound. So for item 1, it is $6. Okay, so divide 60 by 10, and item 2 is $5 because we divide 100 by 20, and item 4 is the value per pound is $4. Okay, so then according to the greedy choice, we are going to put item 1 first into the knapsack, which is this. And then we are going to place the second item because it has the second largest value per pound. And after that, we have quite a bit of room left, but item 3 weighs more than that room. And we can only hold 2 items, and its total value is $160. However, as you can see, that we could also have another packing. So in other words, we put item 20 and item 30 in the knapsack. So there is no room left for this packing, and the total value is $220. So that indicates that the greedy choice doesn't work for 0, 1 knapsack. So the take-home message is this: some problems that greedy choice, the greedy algorithm may not work, but for 0, 1 knapsack, although the greedy algorithm doesn't work, the dynamic programming technique works. So that is the take-home message. that greedy algorithm doesn't always work, although dynamic programming works. All right, so again, for dynamic programming, using dynamic programming for 0-1 knapsack, we follow the same old trick. We formulate a problem, and then we come up with a recurrence relation. So first, we are going to name the problem K, standing for knapsack, and then we use I to indicate the capacity of the knapsack. Okay, denote the maximum. K of I denotes the maximum values of items with the total weight at most 8 pounds. I is the capacity, and hence, since the knapsack can hold up to W, capital W pounds. So what we end up computing is K of W. Now we are going to look at, in order to get KW, so for the knapsack, for these many items, so obviously we want to place one of them. So we want to select AK and place in it such that the remaining, so we choose K so that the remaining items, which is, so the original one minus AK. Okay, so which means that this weighs WK, and the remaining weights, the remaining capacity in the knapsack is capital W minus WK. Hence, this is the this is a subproblem solution, and then the value here we get is WK, and this returns some value. So I don't know which K, but I to choose, but I without looking at all possibilities. So what I'm going to do is I'm going to look for K. So K between 1, K is between, look for all possibilities. K is from 1 to n. Okay, and that's when, well, W is a given. So W is a given, but ultimately that's what it is. And if W, for instance, if W is greater than 0, otherwise, if your knapsack doesn't have any capacity, then K of W would be 0. And since this value is going to change, so it's better to do this by replacing W with an integer I. All right, so this becomes K between 1 and I, and this will be I, so that goes to this formula or formulation. And then we're going to figure out its complexity. And first of all, let's see that, so if we use the original, so KW, right? So the original, before we change it to I's, then we look at all items, so which means K is from 1 to n. And for each selection of K, now there are n choices for each selection, and it's possible to look at now so the weight here is W, so it's a W weight, because we could have the items each weighs for 1 pound. Okay, so so that means altogether you may have to look at n times w many variations at most to figure out this recurrent to figure out a solution to this recurrence relation. Hence, that is the time complexity for 0, 1 knapsack. So the take-home message is that the greedy algorithm doesn't always work, but dynamic programming works. Okay, so I am stopping here, and we'll continue this topic next time, where we're going to work, and we're going to look at Huffman codes. How to use, we're going to look at how to use greedy algorithms to figure out the minimum prefix code. That's the end of this video. Thank you for watching.